Okay, students, have a good day. So today we are going to see about the different types of semiconductors based on the energy band gap. So normally these semiconductors can be classified based on their purity as intrinsic and extrinsic semiconductor. So in the first class we have discussed about the classification of conductor, semiconductor and insulator based on the valence band electrons or valence electrons conductor, and this is semiconductor. So and also based on the energy gap. So with respect to the energy gap, the valence band and conduction band are overlapping in the case of conductor, but in the semiconducting material there is a small energy gap there, and with this energy gap itself there are two different types. They are called as direct band gap semiconductor and indirect band gap semiconductor. So let us see the difference between them. So here in this case the electrons in the valence band aligns well with the conduction band. Okay, so they have a very good momentum, but here you can see the valence band and the minimum energy level of the conduction band are misaligned, but here the minimum energy level of the conduction band is aligned well. Okay, and here the recombination takes place. That means the electrons and hole recombine at the energy gap. That recombination takes place. The first one is direct band gap. Yes. So it happens directly. So it is happening directly. But here it will happen in certain sites, and that are called as traps. So here it is happen directly, and here it is in the traps. Okay, so look at the second point. So this you keep in mind. Directly the recombination takes place. Here it is in the traps in such certain site. You can write that point too. So in a direct band gap semiconductor, so a direct recombination takes place, as I said. So that is the energy released during that recombination, that is equal to the energy difference between the recombination particles. And here you see the relative difference between that. So the momentum is conserved as per the law of conservation of momentum. So there is a relative difference in momentum. So as we have discussed in the first, because of the misalignment. So after that alignment of that momentum only, the recombination takes place, and there is a release of energy. So there is a slight difference between these two, and the probability of radiative recombination is high here. Here it is comparatively low. Since it is directly recombination takes place, it is high, and here it is low. And the efficiency factor of the direct band gap semiconductor also high. So this is high and this is lower. And the example for the direct band gap semiconductor is gallium arsenide, and here it is silica and germanium. And one more point is there, during the recombination, what happens means here the photons will be emitted, and here the heat is emitted. So hence they are used in different application. So since they are producing photons, these gallium arsenide types of semiconductors are used in the making of LED, light emitting diode, but here it is used in normal diode, IC, or transistor, etc. Okay, so this is how the misalignment is mentioned here. So here you can see, so here there is a misalignment of the momentum between the valence band and conduction band for the indirect band gap semiconductor. Hope you understood that. And these things we have already discussed, that is the type of electronic materials based on the energy band gap diagram. So they are conductors, semiconductors and insulators. So you know that all the metals are very good conductors. So the charge carrier there is electron, and in semiconductors the charge carriers are both holes and electrons. So just a recall. And this is a poor conductor, it won't conduct a lot, so they are used as insulator. So you know the corresponding examples also. So these are the energy band diagrams. So this is in the first class itself I have explained these things. Okay. Now Fermi distribution function. So what is first, before that, what is Fermi energy? So Fermi is the name of the scientist, and Fermi and Dirac they proposed a statistical model to arrange this electron with respect to their energy in different energy level. So that is called as Fermi-Dirac statistics. There are different statistics out there: Maxwell, Boltzmann statistics, Bose-Einstein statistics. So atomic energy level, the atoms are arranged in different energy levels. So that is mentioned by MB statistics. So likewise here it is the electron energy level. Now normally the Fermi distribution function is given like this: f of E is equal to 1 by 1 plus e power e minus ef by kt. Let me tell you, for a semiconductor, that is for especially for a normal semiconductor, that is intrinsic semiconductor, the Fermi energy level is exactly in between the valence band and conduction band, and this is given by EF, Fermi energy. The definition for Fermi energy is the maximum filled energy level at 0 Kelvin. At 0 Kelvin, maximum filled energy level. So that is the Fermi energy. So that's why a normal semiconductor that will behave as an insulator at 0 Kelvin. When the temperature increases, it starts to behave like a conductor. So that's why it is said to be a semiconductor. Okay, so this is the Fermi distribution function. F of E is equal to 1 by 1 plus e power e minus ef by kt, and f of E is the Fermi function. E is the energy of the level whose occupancy is considered, and the ef is the Fermi energy, and k is the Boltzmann constant. Okay, so f of E is a function to find the probability of an electron, whether the electron is present in that particular energy level or not. So that can be measured using this Fermi distribution function. Okay, so let us see the different cases of this E and EF. When energy level is greater than Fermi energy, when energy level is less than Fermi energy, when the energy level is equal to Fermi energy. So what are the possibilities for these cases? Let us see one by one. So as I said, Fermi energy, what is this? It is the maximum energy level filled, okay, at 0 Kelvin, the electron filled state. So அதுக்கு மேலே வந்து it will be vacant. Then Fermi energy level, right? Fermi energy level is that particular energy level at 0 Kelvin. So this carrier concentration we will discuss in another day. So that is related to some density of states, so that we can discuss that. Now the effect of temperature on the Fermi function. So as we know, the Fermi function f of E is equal to 1 by 1 plus e power e minus ef by kt. So first case is E less than ef. That means ef is here, the energy you have chosen, that is below that. Okay, so the Fermi energy, below Fermi energy, so the valence band will be here, conduction band will be here. So below this Fermi energy, mostly all the energy levels are occupied by electron. So you know that logically all the whatever the energy level you have chosen, the electrons will be present there. Okay, so here f of E is equal to 1 by 1 plus e power, since E is lesser, so e power minus ef by kt. So this you will get some value like k into T. So the temperature is 0, so 1 by 1 plus e power e minus ef by kt. So minus value divided by 0. So minus something divided by 0. So anything divided by 0, that is infinity. So 1 by 1 plus e power minus infinity. So e power minus infinity exponential of minus infinity, that is equal to 0. It's not infinity, this is 0. So when it is 0, 1 by 1 plus 0, it becomes 1 by 1, and that is equal to 1. So the probability of finding an electron below the Fermi energy level, that is 1. So there is a 100% chance of finding the electron. Okay, so first one, the E less than, so இப்போ E greater than EF. So இதுக்கு மேல வந்து பார்க்கிறோம். So EF, you know the maximum energy level. So this is also 0 Kelvin. At 0 Kelvin, the maximum energy level occupied by electron, அதுதான் என்னது EF. ஸோ அதுக்கு கீழே உள்ளதை எடுத்துருக்கோம். ஸோ கண்டிப்பாக அங்கே எலக்ட்ரான் இருக்குது, இதுக்கு மேலேனா இருக்காது. இப்போ இங்கேயே உங்களுக்கு தெரிஞ்சிருக்கும். ஸோ the probability should be 0. Okay, so E greater than EF. So here also at 0 Kelvin, so that will become 0. So e power plus infinity, so that will become infinity. So 1 by 1 plus infinity, 1 by infinity, that is equal to 0. So in the second case, there is a 0% chance of finding the electron. And in the another one case, we are not taking that temperature is just 0. We are changing the temperature from 0 Kelvin to other temperatures like T1, T2, T3, etc. Now, what is the case when E is equal to EF? What is E is equal to EF? So e power E minus EF, that will becomes 0, and the bottom is also, so in the bottom you have even if you have any value, so 0 divided by, it is also 0. So 1 by 1 plus e power 0 is equal to, e power 0 is 1, so 1 by 1 plus 1, that is equal to 1 by 2. So when it is equal to EF, there is a 50% chance of finding the electron. Okay, so here you can see this is at T is equal to 0 Kelvin, this T1, T2, T3. So based on that, you can see the change in probability here. When the temperature changes, the probability also value also changes. Okay, so bear with the other sounds in between the video. Okay, so here there is a 50% chance of finding the electron. Okay, so at very high temperature, when the kT is greater than EF, so T is tends to infinity. So in this case, electron lose their quantum mechanical character, and the Fermi distribution function, that is, reduces to classical Boltzmann distribution function. So it won't behave like the normal electron, so it will be highly accelerated. So the Fermi distribution function is no longer used here. So what are the uses of this Fermi distribution function? So it can be used to find the probability of an electron. So probability of finding an electron in different energy level at a given temperature. So that is the first one. And you can find the free electrons per unit volume at a given temperature. And it can also be used to find the Fermi energy of metal. So that's all. So one more within one more lecture class we can complete that. So that is one of the important topic that I will teach you during the live class, that is chronic and penny model. So that's all for today's session, students. Thank you. You just go through the MCQ and finish it. Thank you.